Hi, Assalamualaikum warahmatullahi wabarakatuh, my students. Madam Ruby here, logging in again for lesson 53. In lesson 1 of chapter 3, you learn about instantaneous rate and differential rate equations. In the second lesson, we learned how to integrate these differential rate equation to become a beautiful and handsome integrated rate law. So now we're going to learn how to determine the order of fraction and how to calculate certain properties or units of value using the integrated rate laws that we have learned how to write and integrate. So we are going to determine the order of fraction involving a single reactant using initial rate method, units of rate constant, half-life based on the graph of concentration against time, and linear graph method. Then we're going to perform calculations using the integrated law equations. The thing that we're going to do is determining the order of fraction. There are 4 methods or 4 ways to prove that that particular reaction is a 0, first, or second order. The first one would be using the initial rate method. The second one is looking at the unit of rate constant. And then when we plot the graph of concentration versus time, we are going to get the half-life from that particular graph. And then the last method is by using the linear graph method, because we know that the integrated rate equation is following our linear graph formula, y equals to mx plus c. So if we plot y, the ln A, for example, for first order reaction against time, we're going to get the slope as a negative k. We should be able to calculate k there from the linear graph. So let's look into all these methods one by one. In order to get the order of fraction using the initial rate method, we need to get data from experiments. So we compare the initial rate at different concentration for experiment 1 and experiment 2. For example, if we have 2 reactants here, A and B, both is going to be having a different concentration for a different experiment. For example 3.3, there are 4 experiments that is done on the same reaction. The concentration of reactants A and B are given for each of the 4 experiments, and their initial rate is also given in the right column. Our task is to determine the rate law by calculating the order of reaction first, and then we have to calculate the rate constant K. Okay, so let's look at what we have to do first when we are given this kind of data. The rate is equals to K A to the power of X and B to the power of Y. So we want to find X and Y and also K. Look at experiment 1 and 2. We are having the same concentration of A. So we are able to get Y. For the concentration of B here is different. So comparing rate 1 equals to K A1 to the power of X, B1 to the power of Y, with rate 2 equals to K would be the same because it's a constant, A2 to the power of X, B2 to the power of Y. So insert the values. 2 over 8 is equals to K. A1 is 0.5 to the power of X. B1 is 1 to the power of Y. And then K is the same, 0.5 also for 2 to the power of X. And this one is 2 to the power of Y. So you can see here that we can make this 1 over 4, and then this is all can be crossed out because it's the same thing. So we are left with 1 over 4 is equals to 1 over 2 to the power of Y. So can we make 4 as 2 times 2? So 1 over 2 to the power of 2, 1 to the power of 2 is also correct. So we put 1 over 2 to the power of 2 is equals to 1 over 2 to the power of Y. So here we know that Y is equals to 2. See? Next, we're going to compare the experiment 3 with experiment 4 because the concentration of B is the same but A is not. So we do the same thing. Rate 3 equals to K, concentration of A3 to the power of X, concentration of B3 to the power of Y. I'm just going to show you this once, and then the rest you can just follow through. A4 to the power of X and B4 to the power of Y. And then we're going to have the rate 18 over 18 equals to K. The A would be 0.5 to the power of X and B is 3 to the power of Y. And then for rate 4, K is 1 to the power of X and 3 to the power of Y. So we cross this out, and this is going to be 1. So since this is basically 1 over 2 to the power of X, 1 over 2 to the power of 0 is basically 1, isn't it? So we are going to have X is equals to 0. So let's write the rate constant. Rate equals to, let's write the rate law. Rate equals to K A to the power of, what is X just now? 0, and B to the power of Y is 2. So basically we don't even have to write A to the power of O. Actually the answer is also this. Okay, now the next question is to find the rate constant K. So what is the value of K? So K would be rate, okay, divide by B, concentration of B to the power of 2. So you can take any experiment that you like. I'm choosing number 1 here. So the rate is basically 2 over B is 1 to the power of 2. So K is basically 2. And then the unit is molar per molar and per second. So this is giving you at least 5 marks if you got it right. Just now, you saw me write down the unit of per molar per second, just like that, right? Why is that easy for me to write it down? Because I remember the units of K that we have calculated in lesson 51. The zero order reaction would have molar per second. The first order would have per second. And we have also derived that the unit of the second order reaction is per molar per second. So when we were calculating using the initial rate method just now, we established that it is rate equals to kb to the power of 2. That means it is a second order reaction, so the unit of k is this one. So basically what I'm trying to say is that you need to memorize the unit for the rate constant. So let's look at example 3.4. How does the unit of rate constant help us answering questions regarding this? The conversion of cyclopropane to propene in the gas phase with a rate constant of 6.7 times 10 to the power of -4 per second is at 500 degrees Celsius. So we are given here a rate constant, and after the rate constant value we are given a unit of K. Can you see the unit of K is per second? So by looking at this unit of K, we know that this reaction, cyclopropane turning into propene, is a first order reaction. Yes, it's as simple as that. So what we are going to do is write the integrated law equation for the first order reaction and get the concentration A after T 8.8 minutes. Given A naught is 0.25. And then for B, we need to find T, time, that we will take to the concentration of cyclopropane to decrease from 0.25, this is A naught, to 0.15 A. So all we have to do is just insert all these values into the formula, and we're going to get the final answer. So here is the answer. You can copy this down in page 85. We know and establish that the order of reaction for this reaction is first order from the unit of K per second. So some of you might ask, which integrated formula we are going to use, madam? The first one or the second one? The answer is you can choose any one of them. So I choose the latter, the second one, ln A naught over A equals to KT. So the K is given to you, 6.7 times 10 to the power of -4 here. The T you must convert into seconds, and A naught is given 0.25. So the A is 0.175 molar. This is the final answer. You're going to get 2 marks for this. And then for B, you are given A naught and A. And then you want to find T. So just give the answer in seconds. You don't need to convert it into minutes. So now we are looking at graphical method. There are 2 graphical methods. The first one is we are going to use half-life graph to determine the order of reaction by plotting the concentration of the reactant against time. So you can use the graph paper provided in your page 87 because we need to plot the data given accurately in order to get the half-life for the reaction. Let's read the question in example 3.5. The following results were obtained from an experimental investigation on dissociation of dinitrogen pentoxide at 45 degrees Celsius. The balance equation is given, and this is the data. Plot graph of concentration of dinitrogen pentoxide versus time, and then determine the order of fraction and the rate constant K. I am asking you here to plot the graph first before continue watching to look at the solution for this question. So this is y-axis. We're going to plot the concentration of dinitrogen pentoxide in molar. So I'm guessing this would be the maximum 180 and 176 would be somewhere here. This is the A naught, right? And then you're going to plot X. This is X axis, whereby you're going to put here T in minutes. I don't need to convert it into seconds. So this would be 10, 20, 30, 40, 50, 60, and 70. So you're going to get a line of curve like this, a curvy line like this. So this is what I am expecting you to get. The A naught is going to decrease by time. So let's look at the half-life and the first half-life and the second half-life so that we can predict and determine the order of fraction. In a normal face-to-face class, I would wait for everybody to finish plotting the graph so that we can discuss the answers together. But today, I'm just going to show you, this is the A naught, 176 that we have plotted here. And then 176 divided by 2 would be around here, 88, right? So 88, when we look at the time at the curve, that would be 20 minutes. Okay, this is the first half-life we are getting. And then the second half-life would be 88 divided by 2, right? It's 44. So when we try to find what is the time when 44 times 10 to the power of negative 4 molar is established, it would be at 40 minutes. So 40 minus 20 is 20. So basically, the first half-life is 20, the second half-life is 20, means this is X and this is X. It's the same length of time, meaning that this is established as the first order reaction. If you're not sure, look back at your page 83 at the last row, comparison of first and second half-life. You can see at the first order reaction, the first half-life and the second half-life is the same, X. Okay, that is what we have established by taking about half an hour to plot this graph of half-life. All right, the second part of the question is to calculate the K. Okay, we know that the formula to get half-life is ln 2 over K. So we want to get K, we just find it from the formula. So ln 2 over half-life, ln 2 is 0.693, divided by the half-life 20 minutes, we got 0.035 per minute. So this is the unit of rate constant per minute, and the value is 0.035. This is a bit of explanation on the graph. Time taken for concentration of dinitrogen pentoxide to change from 176 to 88 times 10 to the power of negative 4 molar is 20 minutes. And then the time taken for concentration of N2O5 to change from 88 to 44 times 10 to the power -4 molar is also 20 minutes. The half-life for the reaction is a constant and does not depend on the initial concentration of N2O5. Thus, the above reaction is first order. For the second question, we're going to just insert and substitute the values of 20 minutes into the formula, and then we're going to get 0.035 per minute as an answer. The second graphical method is using linear graph method. I'm sure you remember when we were learning additional maths in high school, we learned how to plot a linear graph to get the slope, to get the y-intercept accurately. So here we are going to plot the graph for the integrated rate equation in order to get the information that we want to know from the data. Example 3.6 goes like this. Kinetics data for the decomposition of compound F are given as follows. This is the data. Okay, there is one row empty here. It means that we need to fill it with something. What is it? Applying graph method, verify that the dissociation of compound F is a first order reaction and hence determine the value of rate constant K and its half-life. So basically the question have given you a clue saying that it's a first order. So you need to come out with the integrated formula that you can use for this. So for first order reaction, the integrated rate law would be ln A equals to negative KT plus ln A naught. So what are we going to plot? Ln A versus T. So what is this row about? We need to find ln F. So ln F, you press the calculator together with 10 to the power of -5. Okay, here is the data, and then I'm going to plot roughly the ln F here, starting from -8 going down to -10. Okay, since this is this is T, right? So we're going to have 20, 40, 60, 80, 100, 100, until under 180 here. Okay, so you're going to get a straight line like this, because you know that y equals to mx plus c. We are plotting ln f equals to -k t plus ln f naught. All right, so here m is equals to -k. So we need to find k. Therefore, we are going to find the slope for this graph. So you find this y and this x. Okay, for example, mine would be -k equals to the slope or the m. So it would be -9.9 around here, okay, minus -8.65 around here. Okay, that is the delta y. And then the delta x would be 200 minutes minus 40. So that would be negative 7.8125 times 10 to the power of negative 3 minutes, okay, per minute. So this is a negative k, so this negative would also be this one. So I'm just going to take the positive value to be inserted into T half-life, ln 2 divided by k. So half-life would be ln 2 over 7.8125 times 10 to the power negative 3. This would give us 88.72 minutes. So this is how you answer the question by using the linear graph method. You would have to spend a lot of time to plot the graph carefully, because you are going to have 1, 2, 3, 4, 5 data, and that data can be like this, 5. So you have to find the best linear graph that can fit the space of your graph. Use 3/4 of your page 89. Okay. There is one example that is not in your book. This question you can do in your exercise book, and then we can discuss the answers later. And as usual, your task is to do questions in practice 3.2. Here is question number 1. Question number 2, 3, and 4. Question number 5. And question number 6. For graph method, you can straight away go to the tutorial question at the back of the chapter, and there is also 2 graph pages is provided for you. Thank you very much for watching, and I hope you are able to understand what is being discussed. Remember, you also need to work on the practices. Try to plot the graph accurately. We have done determining the reaction order and performing calculation using the integrated rate equations. I will see you again soon in the next lesson. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Bye.